Welcome back, and today I have a really interesting problem for you that involves these dice. And what you'll notice is that I have 3 dice that look fairly normal. They're just normal dice with all 6 sides labeled 1 through 6. But I have one unusual dice, and this dice has 2 sides labeled 6, and the other sides are labeled 2. So I want to ask you a question, and that is, what if I take these dice and place them in my cup that was given to me by a previous math class, and I shake them all up, and I pull one dice out at random, and then I roll that dice. What's the probability that I'm going to end up with a 6? We start this problem with a tree diagram, and you can see here I've already got the branches of my tree drawn. The first decision I have to make is how I'm going to label the tree. So I'm going to label the first branch with either the normal dice, and that is the one that had all 6 sides on it, or the weird dice, and that is the one that had a 6th side labeled twice. Then my second branch I'm going to label with the probability of getting 6 or not getting 6. So one thing to notice about this decision is that I labeled the type of dice first and whether or not I landed on a 6 second. The reason is because once I know the type of dice, I know the probability of getting a 6, but I don't know the other way around. I don't know whether I'm going to get a 6 or not until I know the type of dice that I selected. Once I have my tree diagram drawn, I have to go through and label it with the probabilities. So I go through each branch of my tree, and I ask, what's the probability of that outcome? So notice I had 3 normal dice and 1 weird dice. So the probability of getting a normal dice is 3/4, and the probability of getting a weird dice was 1/4. If I have a normal dice, then my probability of getting a 6 is just 1 out of 6. But my probability of not getting a 6 is 5 out of 6. However, the weird dice was unique, and its probability of getting a 6 was 2 out of 6. And its probability of not getting a 6 was 4 out of 6, because it had 2 sides labeled 6 instead of the others. Now that I have all my probabilities labeled, I have to ask myself, how could I have rolled a 6 in this problem? And you notice there's actually 2 ways I could have rolled a 6. I could have collected a normal dice and then had it roll a 6, or I could have gathered the weird dice and then had it roll a 6. So I'm looking at 2 of my branches that describe how to get a 6 on this problem. Once I have those 2 branches identified, finding the probability of getting a 6 is the same as finding the probability of each branch and adding them together. So my probability of getting a 6 looks like this. I have a 3/4 chance of going on that normal branch, and once I'm going on the normal branch, I have a 1/6 chance of rolling a 6. Meanwhile, I have a 1/4 chance of going on the weird branch, and then once I'm along that branch, I have a 2/6 chance of rolling a 6. Combine these all together, and my probability is 3/4 times 1/6, that first branch of my tree, plus 1/4 times 2/6, that second branch of my tree. I put all those together, and I get our final result, which is 5/24. So notice this technique allows us to think about our problem in terms of branches. What I did was I thought about the first branch of my problem, which is the 3/4 times 1/6, and the second branch of my problem, which is the 1/4 times 2/6. So there's a fancy formula we can use for this, and it says that the probability of event E is the probability of the event E given that F occurs times the probability of that event F occurring, plus the probability of E given that F did not occur times the probability F did not occur. This is exactly what we did when we used our branches. We found the probability of getting a 6 given that we were using the normal dice times the probability of having that normal dice, plus the probability of finding a 6 given that we had the weird dice times the probability of getting that weird dice. This process has a special name that we call conditioning. For a definition, we could say conditioning is finding the probability of an event by adding together the conditional probabilities in relation to a second event. In this case, notice that we're conditioning the probability of finding a 6 based upon which dice we're using. Really, in short, conditioning is drawing our tree diagram and adding up all the branches that end together in the result that we were interested in. So we can see that through the process of conditioning, by drawing tree diagrams and analyzing the different conditional probabilities, that we can figure out what the likelihood is that we'll get a 6 when we roll one of these dice from this jug. But the real question, well, another question is, if I roll my dice and 6 is the result, then what's the likelihood that this dice is the biased dice that had 2 sides named 6 versus one of the normal dice? Can we tell just from the result what the likelihood is that we grabbed the unusual dice versus the normal dice? So looking back at this tree diagram we drew earlier, we're now looking for the probability of getting a weird dice given that we rolled a 6. If you think back to when we first learned about conditional probabilities, one of the ways of thinking of them was that the condition 6 changes our sample space. So if you look at our tree, notice our tree has a sample space of 4 different outcomes, but by conditioning on 6, it's like we can omit or ignore 2 of those outcomes. And so what we're going to do now is we're going to think about the probability of having this weird dice, but only given 2 of the possible branches and ignoring the other 2 possible branches. You notice that our branch of selecting the normal dice and then rolling a 6 has a probability of 3/4 times 1/6, or 3 out of 24. Meanwhile, our branch of having a weird dice and then rolling a 6 has a probability of 1/4 times 2/6, which is 2 out of 24. Putting those together, we'll see that our total sample space has a probability of 5 out of 24. So our total probability of being in one of these 2 branches was 5 out of 24, which is the problem we found from the previous exercise. So the probability of having the weird dice, given that we rolled a 6, is simply the probability of being on that weird 6 branch divided by the probability of both branches combined. But looking at our results from earlier, that's just the probability of being on the weirdness 6 branch, which was 2 out of 24, divided by the total probability, which was 5 out of 24. Doing a little bit of algebra results in 2/5, or 0.4 as our result, or our probability. So, rolling these dice, once we see a 6, we realize there's a 40% chance, or 2 out of 5 chance, that we actually had the weird dice in our hand versus the normal dice. Notice how this worked. This means that we started the dice, when we pulled it out of the cup, we only had a 1/4 chance that we were holding the weird dice in our hand. But once we roll it, and once we get a 6, now our probability is a 2 out of 5 chance. So the probability of it being the weird dice increased. We're not guaranteed that it was the weird dice that we pulled out of the cup, but the probability that it was the weird dice became larger. It went from about 25% to about 40%. This is the big idea of a theorem that we call Bayes' theorem. And Bayes' theorem is, in short, this process of dividing the branch we're looking at by all of the branches that end up in the given outcome. But we have a fancy formula, so let's write it down and talk about it. So the formula for Bayes' theorem can be written as follows. You start with the probability of f given e, and in our example this was the weird dice given a 6. And we used the formula from earlier, the conditional probability formula, which said this is equal to the probability of f and e divided by the probability of e. Then what we do is we think of the probability of f and e using the multiplication rule, which says this is the probability of e given f times the probability of f. And then we think about the probability of e using the total probability rule from earlier, that we add up every branch that ends in e. So it's the probability of e given f times the probability of f plus the probability of e given f complement times the probability of f complement. And what you'll notice is that this formula describes exactly what we did before. And that is that we have on top the probability of the branch that ended in the result we are interested in, getting a 6, given that it was the weird dice. And on the bottom, we have all the branches that end in a 6, no matter whether they're the one we're looking for or not the one that we're looking for. This process of using Bayes' theorem is really powerful because it lets us look at the outcome, in this case rolling a 6, and ask questions about what had to have caused that outcome. It lets us think about the probabilities of which dice we had, or which outcome it was that caused us to get a 6. So we can say we got a 6, now is it more likely that we had the weird dice or normal dice? How have those probabilities changed from what we originally thought they were? And this is really the real power of thinking about mathematics in a Bayesian way. So if you like this, there are entire fields of math that you can study. It's all Bayesian statistics. But the big idea of Bayesian statistics always follows the same process. We start with an assumption, in this case, that the normal dice had a 3/4 chance of arising, the weird dice had a 1/4 chance of arising. We look at the outcome, in this case the outcome was we rolled a 6, and then we go back and we update those probabilities. And instead of our weird dice having a 1/4 chance, we've now updated it, and our weird dice now has a 2/5 chance of arising. So we take an initial assumption use the information given to us, and update our assumptions. Notice this is a real valid way of thinking about the world, not just in probability, but especially when we have probability and numbers to work with. It turns out that this process of using Bayes' theorem, the idea of updating your probabilities based on what has happened around you, is really common throughout the world of mathematics. And not just for trivial problems like rolling dice, but for really important problems, like problems in medicine where you're trying to determine the likelihood that someone has a disease based on the results of their tests. Or in the world of law, when you're trying to determine the likelihood that someone was guilty of a crime based upon the outcome of different tests, like a fingerprint test or a DNA test. So at this point, we have a practice problem, or a quiz, based on another kind of trivial example, and we'll do some more practical examples when we get to class. For our quiz, I want to ask this question that's in our notes. A student is pretty good at attending class when it's not raining, but struggles to attend class whenever it does rain. In fact, the student attends class 95% of the time when it does not rain, but only 50% of the time when it does. Suppose the weather forecast indicates there's a 70% chance of rain tomorrow. What's the probability the student attends class? And if the student attends class, what's the probability that it rained? So I want you to go through these two questions. Try to do them the same way we did the dice problem. Draw yourself a tree diagram, then look for every branch that ends up with a student attending class, and then do Bayes' theorem and divide the branch that we're interested in, the student attending class and it raining, divided by all the branches that ended up with the student attending class. So I want you to tackle this problem, try it out in the quiz, and see how it goes. Well, I hope the quiz went well, but if you struggled, that's okay. Let's talk through the answers and see if they make sense. So we start with our tree diagram, and the first thing we do is we label it. And we label it with raining and not raining, and attends and does not attend. Notice I put the raining and not raining first because whether the student attends or not depends upon whether it rains, not the other way around. So always think of the order of our tree by asking which event depends upon the other event. And the one that depends upon it should go second, and the one that causes it should go first. So the rain is causing the student to attend or not attend. So that makes the rain the first one in our tree and the attending the second one in our tree. Once we've done this, we want to add our probabilities. And some of these probabilities we had to think through ourselves. Notice we were given that there was a 70% chance of raining, but we weren't told the probability of not raining. But it's just 30% because we know the two branches have to add up to 100%. Similarly, we add all the probabilities for attending and not attending. Now, to do part A, we simply have to look for all the branches that end up with the student attending class. That ends up being our top branch, which is it raining and attending, and this branch here that ends up with it not raining and the student attending. We put those together, and our solution to part A ends up being 0.7 times 0.5 plus 0.3 times 0.95. And when I put all that in my calculator, I get 0.635 as our answer. Not a very good likelihood. I hope you attend class more than this. Now to do part B, we're looking for the probability that it rained if the student has attended class. So what we need is on top of the fraction, the probability that it rained and the student attended class, which is 0.7 times 0.5. And on the bottom, we need all of the probabilities that the student attended class, which is 0.7 and 0.5 plus 0.3 and 0.95. Now, if you're paying attention, you'll recognize that the bottom is simply the problem we did a second ago. So I could have skipped writing all that down and just wrote 0.635 as my answer. The top, we have to calculate, which comes out to 0.35. And then when we divide those two together, we get 0.551 as my answer. What does that mean? That means if the student is sitting in class, there's about a 55% chance that it rained outside. So notice that when the student attends class, it doesn't mean for certain that it didn't rain. The student does attend sometimes when it rains. But what it means is that the rain originally had a 70% chance occurring, but now that we see the student, I ask myself, did it rain? Well, the odds are a little bit lower. The odds are actually only at 55% that it rained once I see the student in class. So that's how we use these ideas of conditional probabilities, and especially Bayes' theorem, to draw conclusions about what's happened given observations like the student sitting in class and the likelihood that it rains. So I hope you found Bayes' theorem interesting. I hope you were successful in the quiz. And if you have any questions, bring them with you and we'll talk about them when we get back. See you soon.